All right, welcome to Chem 395, Experiment 4, X-ray diffraction and fluorescence. Uh, in this video, we will learn how to calculate the theoretical intensities for X-ray diffractogram peaks. So I will be using the data from our previous exercise where we index the calcium metal, and we've obtained all the information that we need about the structure. So here, before we start, I would like to mention a couple things first. The first one is that it's a good idea to keep your calculation clean using different spreadsheets. So in this case, I have one spreadsheet for the indexing, one spreadsheet for the intensities. You can also merge them together, but make separate spreadsheets for different samples for each of the metals and also for your binary salt calculations. That will make it easier for you to keep track, and it will make it easier for the TAs and other people to read your spreadsheet and understand what's going on. All right, the other thing that I also need to mention before we start is that in this exercise, we will make use of the solver add-in on Microsoft Excel. And it is not enabled by default, so what we need to do is to go to File, Options, and go to Add-ins. Here, say that you want to manage the Excel add-ins and go, and make sure that this checkbox on Solver add-in is checked. And once you click OK, it will enable Solver, which will appear under Data here. And we will make use of that later. Okay, so let's start with the calculations. Here again, I've taken the liberty of taking the important equations from the handout here, which we will use, an important table. And also in the intensity calculations, we will need to use this particular formula where F is a scattering factor for the metal of interest. And if you see, F is calculated in this way, where F0 needs to be taken from a table. So again, I've also taken the liberty of taking a screenshot of where you can find it. So this is labeled in the course website as scattering factors. And if you open it, it's going to be a PDF. And here, the scattering factor is given for each of the element, and you just need to find the corresponding value. It depends on the angle. So we will need to calculate something, check what is the corresponding scattering factor, and plug it into the equation. So we will do that. Okay, so here, this is the data that we also used for the indexing part. We have the two thetas in degree. Just to make things faster, we also know the m² value for each of the peak. And here, I also compiled the observed intensity. So in your X-ray diffractogram data, this is going to be your y-axis values. All right, so without further ado, let's just jump into the equation. So first, if we check this equation, we see that we will calculate a lot of cosine and sine, so it's not a bad idea to convert 2 theta into radians and also calculate theta. So let's do that. So 2 theta in radians. It's going to be radians of the angle. All right. Here we also have theta, which is also needed in radians. So let's just calculate that, which is just 2 theta divided by 2. Right. All right. So now we have these two numbers, and we can calculate all the formulas that we need. The next step is we need to calculate the multiplicity of the plane. So here, before we do that, we need to understand that each of these Miller indices, they correspond to the three HKL values, right? So if you look at table 1, you will be able to figure it out. So here, for example, 3 corresponds to an HKL value of 1, 1, 1. 4 is 2, 0, 0, and so on and so forth. So we'll just fill this table. You can always look it up in table 1 on the handout. Here we have 4, 0, 0, and 4, 2, 0. All right. So now we need to check what is the multiplicity of each of this plane. Now, the multiplicity arises from the fact that if you turn each of this number negative, so for example, if I have negative 1, 1, 1, or 1, negative 1, 1, the diffraction angle coming from that plane is going to be the same as the 1, 1, 1. So it will add to the intensity. That's why, for example, here we have 2 possible sign for each of the ones, and we have 3 ones, so that's going to be 2 times 2 times 2. So that gives us 8, which is exactly what we have here. So going by the same principle, and knowing that the negative of 0 is 0, so we can just check the table 2 for each of this HKL value and get the MHKL. So in this case, 200 is an H00 type plane, so it's going to be 6 multiplicity. 220 will have 12. 311 will have 24. 222 will have 8. 400 will have 6, and 420 will have 24. All right. So now the next thing in the formula is we need the scattering factor, which is given by F, and F, we need F0. So to calculate F0 on the table, to obtain it, we need to calculate first sine theta over lambda. Okay. So now let's calculate it. It's going to be equal to sine of theta divided by the lambda. And here, you should notice that the table given in the reference uses the lambda that is in angstrom. So you have to use angstrom for your lambda, because otherwise it will not make sense. All right, so let's do that. And let's copy it down. So when you want to compare this to the table, I would suggest that you use number, which will automatically give you 2 decimal places, because that's what the tables have. And it will make your life easier rather than trying to round it yourself. Okay, so now what we need to do is we go to obtain the F0 value. We need to go to the table, look at 0.15, and see what the table gives us. So here, this is calcium, and this is the sine theta for lambda. So if I look at 0.15, I get the value 15.723. And next one is 0.18, so I go back to the table, and it gives me 14.859. So you can keep doing that, but just for the sake of simplicity, I have all these values here compiled previously, so I will just plug it in. Now, there is one thing that you might notice is that not all of the values that you get here will be available on the table. For example, 0.31 here is not anywhere on the table. So I have 0.30 followed by 0.32. So what you can do is to estimate what the value should be for 0.31, you just take the nearest neighbors and just average them. So it should be in between these 2 values. And that's exactly what I do here. So I take the values for 0.30, I take the value for 0.32, and I average them. and that's my estimate for 0.31, assuming linear behavior in that interval, which is not bad actually, right? Okay, so now we have the F0, but this F0 assume that you have no temperature dependence. Like you assume that the crystal, the atoms in the crystal are not vibrating, which is not true because we are doing this experiment in room temperature. So to take that into account, we need to use this formula where there is this exponent term which will give us the temperature dependence. And B here is the Debye-Waller factor or constant. And that is something that we will have to play with. So I will start with a value of 1.5, which is normal value for inorganic crystals at room temperature. So now let's calculate F. Okay, so F is going to be F0 times exponent of minus B. So I will lock it because it's going to be the same, times, so it says sine square over lambda square, which we already have here, and we just need to square it. All right, so that's going to give us the value of F at 1.5. And you can see what it does is it decreases the scattering factor compared to the F0 value. So if I try to increase this to 20, just to go to the extreme, all of my scattering factor will be very low. So let's just go back to 1.5. Right? All right, so we figured out what is M, what is F, and now we just need to calculate the rest of the expression, which is pretty simple, as long as you don't make any careless mistake. So let's just go through it one by one, just to make sure we're doing this properly. Of course, again, you can do this in one shot, but if you're not comfortable with doing that, I would recommend that you calculate each term separately and then just do a big formula in the end. Okay, so first let's calculate the numerator. So 1 plus cos square of 2 theta, which is going to be 1 plus cosine of 2 theta, which we already converted to radians here, squared. Simply that. Right? Now let's calculate the denominator, which is sine squared theta times cosine theta. All right. So that's going to be sine of theta and square it, multiplying cosine of theta. And there you go. Okay, so let me mark the columns that we are interested in. So we have M, we have F, we have the numerator part of the angle dependence and the denominator part of the angle dependence. So just to make sure, let's do that. Right, so now the intensity of each of my pick, oops, let's make that normal, is going to be M times F squared times the numerator divided by the denominator. All right, so that's the intensity. But now, as you can see, it's very hard to compare this directly to the observed intensities that you have. So what we need to do in the next step is we need to normalize it. So let's say that this is calculated and normalized. So it's doing that for everything. So let's make sure that all the cells are normally formatted. Okay. So now it's going to be this divided by the maximum value of the whole range. And again, you can press F4 and it will lock the range that we're interested in. So of course, the first pick is very intense. It's going to be 1, and everything else will be less than 1. Okay. Again, just for the sake of presentation, it's nice to just keep a few decimal places. Don't overdo it. Now here, for the next one, we need to calculate the observed normalized intensities, which again, we'll just keep the same formula, but now we will use the observed value. So it's going to be this divided by the maximum of the entire range. So there you go. Lock. Okay. All right. So again, copy down, and again, let's use number and increase it maybe by 1. All right, so if you compare it side by side, looks like we got a pretty good agreement with what the experiment says, right? Some is a little bit too high. At some point, you get some values that are a little bit too low. So what we need to do is then play with the bipolar value and see if we can get something that's as close as possible to the observed intensities. Now this is where we will play with solver because it can do that for you automatically. So now we will take a look at this expression here to calculate R, which is the sum of the absolute values of the difference between your observed and theoretical intensities, normalized of course, divided by the sum of the observed intensities. So as you can see, this is a measure of error. If you have a perfect match, your numerator will be 0. So we want to minimize the R value to obtain the best match. So first, let's calculate the difference, or I should say the absolute difference, which is simply absolute value of the calculated minus the observed. Again, because this is an absolute value, doesn't matter if you calculate observed minus calculated or calculated minus observed. Okay, so we have that. Of course, the first pick is going to match because it's going to be the most intense, but we will have disagreement in the rest of the pick, right? So now R is simply calculated as the sum of these differences divided by the sum of the observed. So make sure that you do it properly, not the sum of the calculated intensities, but the observed intensities. Okay, so now we have a value of 0.08. Okay, maybe let's give it one more decimal place so that we can see. Now, if you see, I can play with this and I can make it bigger or smaller, right? And of course, you can see here, for example, if I start from 1.5, I go to 2, my R value is getting smaller, but if I increase it to 3, oh, it's getting bigger again. So it looks like the right value is between 1.5 and 3. And of course, you can scan it a little more carefully, 1 by 1, 0.1 by 0.1, and then 0.01, and then decreasing your threshold. But we can automate it with the solver. So let's start with 1.5 because that's the value that we had. So now we need to go to data and to solver. And now this dialog box will pop up, and I've already set it up, but let's go through it one by one. So first here, when it says set objective, we want to, that's the cell that we want to minimize or maximize or whatever. So in this case, this should be our R value, and we want to minimize it. And as you can see, you can just read it, and it's actually pretty clear. It says set objective, the cell P10. I want to minimize it by changing, and you can say I want to change my B, which is in J here. Okay. And now you can also add constraints. For example, in the handout, it says that you can add it, and you can say that the B value has to be greater or equal to 1.5. So it will not go under 1.5. Okay. So you can add another one, which is my B value should be less or equal to 20, because otherwise it's going to be a very hot measurement, and we did not have that. Okay. So if you click OK, it will go back to the previous dialog box, and it's all set here, the constraints. All right, so you can leave the rest of the settings as is, and you can just click solve. And if solver found something, it will actually change the value. And what you want to do is then keep solver solution and click OK. And as you can see now, my B value has been changed into something totally different from 1.5. And as we saw before, it is located between 1.5 and 3, which is, yeah, but now this is much more accurate. So this is what we have seen, and we see that the R value is now less than 0.08. Now it's 0.07, let's see. And that's as good as I can go. Yeah, maybe you will start with a value of 0.1 or 0.2, but solver will definitely help you find what is the value of B that will give you the best match between your calculated and observed intensities. Okay, so that's how you do the intensity calculation for the metal, and how to obtain the optimum value of the Debye-Wohler coefficient to get the best match between calculation and observed intensities.